Hey guys, welcome back to part four of relearning machine learning, and in this one we're going to be covering neural networks, which is something that Andrew decided to cover in coincidentally week four. Um, I think by now most of us will be quite familiar with what a neural network is. If you don't, a neural network is basically um, almost like the second wind that led to the boom in machine learning that we see up until now. Um, Neural networks are these sort of software constructs that sort of aim to mimic the way our human brains work. So we've got artificial neural networks, which sort of describe the machine learning neural network, and then we've got biological neural networks, which sort of describe the actual brain. So Andrew, he sort of starts with the idea of why. Why do we look at neural networks? Why is this something important when we've already learned about, logistic regression, and classification and linear regression. And the thing is that sometimes these things are good, but just due to the way that you actually formulate the problem, um, it turns out that it's not always so suitable because sometimes the number of features you have go into um, thousands or even in the millions. The example that he uses is for images, which is quite a popular sort of uh, I guess form of machine learning. It was probably the more popular form that drove the initial wave of machine learning in the sort of recent decade. And the thing is, like when you have an image, um, as I've sort of alluded to, you've got, thousands or even millions of pixels going in. Logistic regression just isn't meant to handle that. You've got too many features for possibly the amount of data that you have. So you need a new sort of a processing method, a new processing method to do this, which is where neural networks come in. They specialize in handling, this large, um, almost arbitrary amount of features. So um, I guess at a low level, if we get into the details of, what this neural network is trying to do, we should go back to basic biology. Now, oftentimes, people explain neural networks by linking back to biology, but the truth is that this analogy only takes you so far. Like some of this stuff, it will make a lot of sense. The dendrites, the nucleus, and then finally the uh, what is this part called again? Um, the axon. Yep. Um, like this makes sense when we look at this, but if you actually have a really good understanding of how neurons work, and how the brain actually learns, this analogy breaks down a bit. But Um, the key sort of point of this particular image was to look at, the basic format of what a neuron is looking like, and later on we'll compare that to the software abstraction. Um, so, a neuron has these things called dendrites, which are, considered as the inputs. They're what is connected to, other neurons' axons. So there'll be like, neuron 1, neuron 2, neuron 3, neuron 4. And neuron 1 will have axons that connect to this dendrite, and neuron 2 will have axons that connect, and neuron 3 will have axons that connect, and so on and so forth. So this is taking stuff in as input. Um, there's then, a nucleus, which does some things, and actually what it does is it collects um, the strength of the signal that it gets from this dendrite, and it decides, well, let's say I've got a signal that's 5 dendrites strong, uh, or let's take an arbitrary number. Let's say our signal is 6 strong. Should we, as a neuron fire, should we send our signal off to the next one? And if it does fire, then what happens is, we'll send its signal to the axon. The axon terminals will connect to other dendrites, and that process will continue on throughout our brain. And what does this look like in the software side? Well, it looks something like this. You have these inputs going into, our false artificial neuron, and it sends an output out. Um, it actually sends an output out to this thing called an activation function, which is sort of what decides, sorry, it decides the strength of your firing, so to speak. Uh, and this is actually, well, in our case right now, um, the output function that we use, the firing function, that's not really a terminology, um, is the logistic function. So we've seen this before. It's a 1 over 1 plus exponential of, negative theta t or negative theta transpose x. Um, this is actually called the sigmoid activation function, and we might see later in the CS231 notes, there's quite a few different activation functions. This isn't really used that much anymore. You're more likely to use something like, ReLU, leaky ReLU, ELU even. Um, but this is a good one to start with. It illustrates quite a few of the characteristics that we'll want to keep in mind later. Uh, let's see if I can find a better fully connected layer to explain this. Sorry, something else I've realized I've just forgotten to cover is the idea of weights or parameters. This is actually quite stupid of me because it's really fundamental. So this weights here, theta naught, theta 1, theta 2, theta 3. What it does is, it's very similar to the parameters that we saw for linear regression. It modifies the strength of our input signal. So this could be like, 0.1 or, could be like 2, depending on how valuable, we consider that particular input or feature. So this is a sort of a better example of what normally happens in a neural network. This really, ignore this bottom part here. This really only has one layer. Normally, if you look at a neural network, you don't count the input layer, which would be this one as a layer. And what Andrew has described here as the output layer, basically the activation function, in his case, really uh, normally just it gets included in each layer. Like each layer has its own activation function. Just like, every single neuron would have its own decision on whether or not to fire. Um, so, if you take a look at this, every single um, input piece is connected to every single neuron. This is what's called a fully connected layer. Um, or, there's quite a few names for this. It could be like a multi-layer perceptron layer. It could be a fully connected layer. I think there's a few others as well. And what happens is for each of these neurons, they're going to have, they're going to, like do a summation, a weighted summation of the inputs with the weights. So it'll be like x1 times theta 1 plus x2 times theta 2 plus x3 times theta 3. And that gives you that. And then realistically, what's going to happen is, uh, a bias will be added into this. And it will go through, say, a activation function before it gets sent off to the next one. And another thing to keep in mind is that if you were to have, like separate layers, any layer that's not the first layer or the last layer is called a hidden layer. This isn't so important to know about these days, but I find that it's good, sort of like, it's good to know because you'll see that quite a bit, that terminology. And this slide is basically just going to formalize what I was talking about earlier around the fully connected layer and what that sort of equation looks like. So in this very simplified neural network example, you're going to have this equation basically. And now it looks kind of complex, but it's actually quite simple when you break it down. A1, the value of A1 output is going to look like, um, theta 1 naught, which is basically just saying the weight for, um, sorry, Andrew hasn't drawn an X naught here, but imagine there was another one here. It's going to look like, um, you know, the connection from alpha 1 to X naught times X naught, theta 1 1 times X1, so that's that one there, theta 1 2 times X2, so that's that line there, plus, theta 1 3 X3, which is that line there, and it goes through a function G. G could be the sigmoid, it could be, another activation function. Essentially what that does is it introduces a what we call a non-linearity, um, basically ensuring that your output isn't just going to be, um, a bunch of linear summations, linear algebra. Because if it was linear algebra, essentially the only line that you could model is a straight line. What you really want is you want to be able to model all sorts of shapes or whatever, depending on your data or your problem. And actually, that sort of leads me into another point. Sometimes you don't hear about it so much these days, but in the past, machine learning models used to be called function estimators, because it would estimate the function of your problem. And when you see something like this, and when you sort of abstract all the non-linearities and whatever out, and knowing that it can model any sort of shape, you can sort of understand why it is considered a function estimator. Um, in the next slide, Andrew sort of covers this idea of why neural networks are actually quite good, why they're becoming increasingly popular. It's for a few reasons, but the main one is that compute suddenly became available. But also, it turns out that neural networks have a very favorable thing going for them, which is that they can be vectorized. And if you work in machine learning at like a low level, which is to say that you might be coding your own layers, or um, even if you are just really interested in, I don't know, this style of coding, matrix style coding, this is really interesting. But the idea around vectorization is that you can, do these calculations using matrices and vectors. And in certain languages and frameworks, such as in C, MATLAB, Python with NumPy, um, even TensorFlow and PyTorch, this is a really fast and a really efficient way to do these calculations. But essentially what he's doing is he's writing out the calculations, the matrix calculations that you should be doing, which is to say, um, like theta 1 times x1 is going to give you the output, and then that then goes through a non-linearity function, and then you might add, a bias term in there. Normally it would be like theta 1 x1 plus a naught, and then you pass that in through your non-linearity to get your output. Um, and for like output 3, it could be like theta 2, a2. If you're interested in this sort of stuff, I think we might cover it again a bit later, but have a look on like the vector maths for machine learning. It's actually quite interesting, and it's I don't want to say fun, but it all works out quite nicely, and it's quite a beautiful thing. Just to build on that function estimation piece, Andrew then goes and sort of I actually cut, like, I didn't remember this part and I didn't write it down, but he basically builds out um these neurons as like AND gates, OR gates, XOR gates, and I think NOR gates, basically just to prove that um, you know, using this sort of format, you can actually model quite a few different non-linearities and different patterns, so to speak. So, like, for example, um, what is this one? I think this one is uh, that's a knot. Let's go to the next one. This one would be the AND gate, and you can sort of see it in the graph down here, sorry, in the table down here, where, for certain values you can figure that out. This would be the OR gate, and you can sort of see it in the table that he's put up here. And if you sort of put it all together, you can sort of see the combination to form an XNOR, which looks something like this. And I think with all of these put together, you can basically model, I think it's like almost whatever process you want. And the last thing that Andrew sort of covers this week is the idea of neural networks as classification engines. Basically that they can handle multiple classes by say outputting a vector of values, and using that one versus all idea that we would have seen previously. So the outputs here is like the probability that the output belongs to that class. So in the example we have here, Andrew's probably used uh, something from like a self-driving computer vision model. Um, is your image showing you a pedestrian? Is it showing you a car? Is it showing you a motorcycle? Or is it showing you a truck? And with a pedestrian, your output would look like this, car like this, motorcycle like this, and truck with your, with your one at the bottom position. So I think for that week, that was the last thing that Andrew wanted to cover. The last thing that I wanted to cover is that um, the way you sort of model a neural network or connect the neurons together, the way you sort of uh, structure your layers, the way you put your layers together, the way you connect your different layers together, um, that is what is described as a neural network's architecture. And that's something that you'll see a lot going forward because, most of the modern machine learning stack now is built off this idea of neural networks. And they all have uh, very unique architectures up until the transformer, which realistically didn't need any improving on its architecture. Um, but yeah, that's it for this week or this segment. Um, I don't think we covered too much, but what we did cover was very important. This idea of neural networks. Um, I'd say this is probably the single most important idea going forward. And if you're following along to sort of learn machine learning from scratch, you probably want to, take a moment and actually maybe just look at a bunch of resources on neural networks to make sure that everything that I've talked about, everything that Andrew's discussed, you're comfortable with, because going forward, I think we're going to be building a lot on this sort of information. So in the next segment, we're going to be looking at the cost function as well as a few other things there. Just a word of warning, the cost function is quite mathematics heavy, but it's actually quite rewarding to go through that mathematics because someone else has worked it all out for you, and realistically, um, there's no problem to it. You're just seeing a solution, so to speak. Right. So I hope you've enjoyed this segment. I'll catch you in the next one.